So 7.2 is going to stay with that slope-intercept form of a line. So we know that y equals mx plus b. And the key thing here is that the m is your slope. In 7.2, we're going to talk about relationship between two lines. And we're going to talk about special relationships in that when you have two lines, you could say that they might be parallel to each other. So they run right side by side, or they might be perpendicular to each other. So that means that they intersect at 90 degrees. And so we could have, two lines that intersect at 90 degrees. So we're going to examine the parallel lines first and then the perpendicular. We're going to start with the introduction of this in the first part of the video, and then after the second part of 7.2 is a topic that I find students often have difficulties with. So it might be a video you want to revisit, the second part of 7.2. So starting off 7.2, parallel lines are two or more lines that are always an equal distance apart. Parallel is long, and so if I want to say that line 1 is parallel to line 2, I might write it like that. So it's just a bit of a shorthand here, this little parallel lines, so double slashes. Two lines that are parallel will never intersect each other. They're always going to run right side by side. So they're a lot alike, but they're never going to come together. I kind of like personify them as like kind of star-crossed lovers, and that they're never going to come together, even though they're so much alike. I don't know if you see lines as personalities, but anyway, that's what I think of when I think about this stuff. So if lines are parallel, their slopes are exactly the same. So if we were to take a look at, two lines with the slope of 1, they could run right side by side. And so what we're going to do is, from our understanding of slope-intercept form, when we can see the slope in the equation, that will be our cue to tell us if two lines are parallel or not. So let's take a look at the examples here. So for A, this is line 1, this is line 2. From here, we can take a look at the coefficient of the x term. That tells me the slope. And so this tells me that no, the lines are not parallel because they don't share the same slope. What we're looking for is the m values should be the same if they are parallel. Okay, so B, line 1 and line 2, when I take a look at these two equations, I can see that they have the same m value. They have the same coefficient on the x term. And so that tells me that, yes, the lines are parallel. For C, when I take a look at line 1 and line 2, two different equations, but I understand from my slope-intercept form that that is defining the slope of my line. And if they aren't the same, then no, the lines are not parallel. And the last ones down here, if I take a look at line 1 and line 2, they both have a coefficient of 5, but one is positive and one is negative. So no, they are not parallel. So all we're doing when we're comparing two lines in slope-intercept form is looking for the exact same coefficient on the x. And from that, we could say that the two lines are parallel. So from these ones, if we have a bunch of information, now we're supposed to determine if line 1 and line 2 are parallel. So it does say, recall the slope formula. So we knew that slope, or m, equals y2 over minus y1, all over x2 minus x1. That was from back in chapter 6. And so for each of these lines, we could calculate the slope. And from that information, say if the two lines are parallel or not. And so I like labeling these up because I'm good at making mistakes. Oops, sorry, x1 and y1. Remember, because they're from the same point. x2, y2. And then my slope for line 1 would equal 6 minus 3 over 4 minus 2. My slope is equal to 3 over 2 for line 1. For line 2, if I take a look at that, again, following my format, and I think it's worth labeling up my points because I'm good at making mistakes. I'd have 8 minus 2 all over 0 minus, minus 4. Anytime it was a negative, back in chapter 6, I was subbing in with brackets and sort of skipping the subbing in with brackets if it was a positive number. So I'd get a final answer of 4 over 4. And I can simplify, 6 over 4. Let's try that again. 6 over 4. And I can reduce that or simplify that if I divide the top by 2 and the bottom by 2, I could get that my slope is 3 over 2. So what I'm doing with these is comparing the slopes. So those 2 points, those 4 points, 2 on each line, gave me the information to say that yes, L1 is parallel to L2, or the lines are parallel, if you'd rather put it in words. Another one to try there. I'll just let us work through this one. So line 1 and line 2, again, what we're going to do is calculate the slopes and then compare them to make this conclusion or answer is like, are the lines parallel or not? So for line 1, I'm going to calculate the slope. So I get a final answer here of 5 over 3. Oh, shoot, what did I just do? Did I miss a negative? Oh, I put a negative in when I didn't need one in there. Oh, there we go. Okay, so 5 over 3 is my slope for that one. And then line 2, my slope would be 8 minus 4 all over 0 minus 3. So I get an answer of 4 over 3. Well, these two slopes are not the same. And so if the two slopes are not the same, that means that line 1 and line 2 are not parallel. We're going to give a similar treatment to perpendicular lines. So those were parallel lines. And for parallel lines, we're looking for the exact same slope. For perpendicular lines, I went over before that the two lines intersect at 90 degrees. And so the shorthand for that is just that sort of T sort of upside down shape. If the two lines are perpendicular, their slopes are reciprocal to each other and have opposite signs. So in other words, the textbook says they are negative reciprocals. So that means upside down opposites. Again, that's not textbook speak, that's sort of what I think. So in this one, if we go through these examples, we can take a look at that. So if line 1 had a slope of 2, which we know is 2 over 1, line 2, if it was perpendicular to it, would be an upside down version of that fraction. And because this was positive, this is negative. So those two slopes would be perpendicular to each other. Working through the next one, I see that one slope for line 1 would be negative 3. I know that that is negative 3 over 1. So perpendicular to that would be the upside down opposite of that. The next one, negative 1/4. Upside down opposite would be a positive 4 over 1. The last one, maybe easiest to see, the upside down opposite of 2 over 5 is negative 5 over 2. Give these ones a try. So these ones are saying, okay, if line 1 is this and line 2 was perpendicular, what would be the slope of that perpendicular line? Give them a thought. I'll throw the answers in. I do think that sometimes thinking this through in your own words, so upside down opposites, is somehow useful. The other thing is that it can be useful to write the fractions where you see the whole numbers, because that allows you to see how they really are upside downs of each other. So now that we have these ones, just from the equations of the lines, it says, are these two lines perpendicular to each other? So what we're looking for is upside down opposites for what's in the M place. And so for A, line 1 is defined by that equation, line 2 by that one. And when we take a look at those M values, line 1 would be perpendicular to line 2. So yes, that's a good one. For B, I've got line 1 and line 2. And when I look at them in slope-intercept form, I can see they actually have the exact same slope. So they're not perpendicular. These two are actually parallel. So we could add that in. Lines are parallel. But that's not answering the question. Just wanted to know if they were perpendicular. Okay, next one. C, if I take a look at that one, they're not upside down opposites. They are not perpendicular to each other. Again, they're actually parallel to each other. And D, if I take a look at this one, that's good. Line 1 would be perpendicular to line 2. So we're going to give the perpendicular lines a similar treatment to what we did with the parallel lines. And so in these ones, again, we're going to solve for slope in order to determine if these two lines are perpendicular to each other. I think it's worth, if you like, you can write out your slope equation again. And really what we're supposed to do is sub in to solve for m in each case. When I solve for their slopes, I can then see that yes, the lines L1 is perpendicular to L2. The last ones, solving for their slopes. Reducing when I need to. I can see that they are actually upside down opposites of each other. So line 1 is perpendicular to line 2. So the next ones are going to give us other pieces of information about two different lines, and it's going to ask, are the lines parallel, perpendicular, or are they neither of those things? Because we know if they're parallel, they have the same slope. For perpendicular, they have the upside down opposite slopes. And so in these ones, I think the easiest way to get there is to put it into slope-intercept form from the standard form. So in each one of these, I'm going to put into slope-intercept form. So I'm going to put y equals mx plus b. So solving for y, I'd subtract 3x from both sides. I'd get 2y equaling negative 3x plus 4. Finishing up to solve for y, I get that y equals negative 3/2 x plus 2. I'm going to take a look at the other equation here. I'm going to subtract 6x from both sides. I'm going to have 4y equaling negative 6x plus 12. Divide both sides by 4. So I get my final equation in slope-intercept form of, check this one out, you can reduce the negative 6 over 4 to negative 3 over 2. Might take you a second to catch up on that one. Plus 3. When I take a look at these two equations now that I've put into slope-intercept form, what I'm doing is comparing those m values, the slopes of my equations. And so when I see that they are the same, I would say that the lines are perpendicular. You can write out the word perpendicular or you can use the symbol. So the bottom two here, again, what we're going to try and do is put them into slope-intercept form because that's the quickest way that I can compare their slopes. I would add 3x to both sides in this first equation that I see in B. I get 2y equaling 3x plus 4. Divide both sides by 2. and I'd write it as y equals 3 over 2x plus 2. Taking the other one and giving it similar treatment, solving it for y, subtracting 2x from both sides. And again, once I've got it in slope-intercept form, it's so useful. Now I can see those m values. Now I can compare them with what I know. Are they the same? Are they upside down opposites? Or are they something else? In this case, they're upside down opposites. And so that information is what can tell me that the lines are perpendicular. So we've got one last kind on these. One last kind, and this one down here is actually a bit of a bonus. This one is particularly difficult. So we're going to end the video, but I'll give you the heads up that this one's a little bit awful to do. So this one, again, gives us some information. Let's see what it says. A line is perpendicular to a line with slope negative 1/2. And it's going to pass through 2 points, negative 1 and 4 and 2 and y. We want to know what is the value of y. Okay, well, this gives us a bunch of information. It gives us some information about an old line and then asks us information about a new line. So the old line has a slope of negative 1/2. The new line is perpendicular to that one. So the new line slope would give me a slope of 2, right? That's the upside down opposite of the old line. Now the other bit of information it gives me is 2 points that it goes through. So once I have my slope here, I'm going to use that slope equals y2 minus y1 all over x2 minus x1 to figure out my missing variable. So this would be x1 and y1. This is x2 and y2. So I know that, maybe I'll just write it all out. M equals y2 minus y1 all over x2 minus x1. My m is my 2. That's what I knew it was. Maybe I should even write it out again. So my y2 is y. That's one I don't know. My y1 is 4, so minus 4. My x2 is 2. And my x1 is a minus 1. So that's just subbing in the information from the question into this equation that we know calculates slope. So now what I need to do is solve for y here. I'd have 2 equaling y minus 4, nothing I can do, but I can tidy up this bottom part. That would be over 3. If we want to get rid of fractions, we know how to get rid of a fraction by multiplying everything through by something that's going to get rid of that fraction or obliterate it. So I could multiply this side by 3 and this side by 3. That's going to allow me to do this really awesome thing of crossing that out. I'd get the next line of my work saying that 6 equals y minus 4. Now that everything is above board, it doesn't look quite so scary. I'm solving for y. And so to get y all by itself, I'm going to add 4 to both sides. So I get a final answer of 10 equaling y, or y equals 10. So we're going to use this similar idea here in that this one is going to do the same thing, except for the mechanics of solving it are way worse. So it's definitely a challenge question. So the idea here is that we have a line is parallel to another line. So this was the other line. And the slope of the other line is 2/3. The line that we're asking about, so parallel to this, the new line, the one that's in the question, the slope is going to be exactly the same because we know, oops, that doesn't look like a 3, we know that a parallel line or parallel lines have exactly the same slope. So we have a new line slope given, and we have, again, these partial points. So this would be x1 and y1. This would be x2 and y2. 2. Again, what I'm dealing with is that m equals y2 minus y1 all over x2 minus x1. Subbing everything that we know in, we know my slope is 2 over 3. We know y2 is 4. We know that y1 is 2. My x2 is 3, and my x1 is x. So once you've got it all put together, the name of the game now is solving for this x here. And it is messy. Let's just take a look at it. So we have 2 over 3 equaling 2 over 3 minus x. So getting this one all on its own, we need to get rid of our denominators. And honestly, this is why it's a bit of a bonus. We've never seen ones that looked quite like this before. So knowing that this is a little bit above and beyond, what I'm going to start by doing is getting rid of this 3 in the denominator over here. So I'd multiply this side by 3, but that means I need to multiply this side by 3. So when I do that, that crosses out, and my next line would be 2 equaling 6, because it's 2 times 3, all over 3 minus x. So the next thing I want to do is, again, keep getting rid of these denominators. Keep getting rid of any of the fractiony bits. And so when I want to get rid of something that's down below, I need to multiply both sides by that thing. So when I've multiplied these by each other, if I write it at the top now, what I've got is 2 times this 3 minus x equaling 6. And once I've got rid of all my fractions, it's a whole lot easier for me to see what's going on. What I'm trying to do is solve for x. So I need to distribute the 2 to get 6 minus 2x equaling 6. I'm going to keep solving for x, so subtract 6 on both sides. I'd get that negative 2x equals 0. And it's really a bit of a bummer because I get that my final answer is that x equals 0, which is super, super disappointing considering how much work that was. So we're going to carry on with 7.2 in the next video. That gives us a bit of a primer into parallel lines and perpendicular lines and reminds us of some of the tools that we have with our slope-intercept form and our equation that calculates slope.